This question is from the GATE Physics paper 2021. This is the MCQ type question having 1 mark. And the question was asked from the topic electromagnetic theory. The question is, consider a solenoid of length L and radius capital R, where capital R is very less than L. A steady current flows through the solenoid. The magnetic field is uniform inside the solenoid and zero outside. So this is the schematic we are given. Among the given options, choose the one that best represents the variation in the magnitude of the vector potential 0, Fi 0. These are the three components of the vector potential at z equals to L by 2 as a function of radial distance small r in the cylindrical coordinates. We are also given a useful information, that is curl of a vector in the cylindrical coordinates. So these are the four options which shows the variation of the vector potential at z equals to L by 2 as a function of radial distance small r. So we have to choose the correct option which represents the variation of vector potential as a function of small r correctly. So let us go to the solution part. So we'll consider a solenoid having radius capital R and length L, and the current is flowing through the solenoid along phi cap direction. The axis of the solenoid is along z cap direction, and as the current is flowing along the phi cap direction, so our magnetic field in the solenoid will also be along the z direction. It is also given the radius of the solenoid is very less than of its length. So basically it will be considered as a long solenoid. Now we know for a long solenoid the magnetic field inside the solenoid will be constant, and that is given by mu naught Ni z cap, where mu naught is the magnetic permeability in the vacuum and N is the number of turns per unit length and I is the current flowing through the solenoid. And in the outside region of the solenoid the magnetic field will be 0. Now current is along phi cap direction. So eventually the vector potential will also be along phi cap direction. We have to find the vector potential. So basically expression for vector potential both inside the solenoid and outside the solenoid. Now we'll consider the first case, that is smaller less than radius of the solenoid. So this is basically the region inside the solenoid. For this we'll consider a circular path of radius smaller at position z equals to L by 2. We'll calculate the closed path integral of vector potential along this circular boundary. Now this line integral can be written as surface integral of curl of the vector potential. And we know the curl of vector potential is basically our magnetic field. So it can be written as the surface integral of B vector. Now inside the solenoid the magnetic field is constant, and that is mu naught Ni. So we can easily calculate this surface integral as mu naught Ni multiplied by pi small r square, where pi r square is the area of the circular region. And also from the symmetry consideration the vector potential will be same along the boundary. So we can calculate this line integral as mod of a vector multiplied by 2 pi r, where 2 pi r is the length of the circular boundary. So our vector potential at position smaller will be mu naught Ni by 2 multiplied by smaller, and in the vector form it will be mu naught Ni by 2 multiplied by r along the phi cap direction. Now we'll consider the second case, that is smaller greater than radius of the solenoid. For this, we'll consider a circular path having radius smaller at position z equals to L by 2. So now our small r is greater than capital R. We'll do the same treatment, and for that we'll take the closed path integral of the vector potential along the circular boundary. and we can write this line integral as a surface integral of the magnetic field. Now magnetic field inside the solenoid is constant, that is mu naught Ni, but outside the solenoid the magnetic field is 0. So we'll split this surface integral into two parts. So one is for inside the solenoid and other one is for outside the solenoid. For inside, the V vector is constant, that is mu naught Ni, and the surface area will be pi capital R square. So this first part will be mu naught Ni pi capital R square. But the second part, the B vector is 0, because outside the solenoid the magnetic field is 0. So eventually this second integral will give us 0. And for the line integral, closed path integral of the A vector, this will be mod of A multiplied by 2 pi r. So our vector potential will be mu naught Ni capital R square by 2r, and in the vector form this will be mu naught Ni capital R square by 2 small r along the phi cap direction. As of now, we have calculated the vector potential for both inside the solenoid and outside the solenoid. So if we see the expressions of vector potential, then the A phi is proportional to smaller for inside the solenoid, and it is proportional to 1 by smaller in outside of the solenoid. So if we plot this plot will look like this. So among the four options, this option C is representing the variation of the vector potential as a function of radial distance smaller correctly.